Hello, everyone, and welcome to lecture 23 of GPU computing. Today will be our final lecture, and unfortunately, because we have a limited time in the course, there was a limited set of topics that we could cover. So there's plenty of other topics that we haven't covered, a lot of patterns that we could have covered that we didn't cover, and also some advanced features of GPUs or other kind of useful things that we didn't cover. So what I will do today is I will just go through a potpourri of some of the remaining features that we haven't covered, so that you guys are aware of it in case you ever want to use features like that, or in case you ever see code that's using these features, so that you know what they are. But we're not going to go into any details about each of them. So we're just going to kind of go through a potpourri of remaining topics that we haven't covered, and conclude with that. Okay. So this is the kind of list of topics that I'm going to briefly touch on today, and so we'll get started with we'll go through these in order. So we'll get started with multi-GPU programming. So multi-GPU programming, we can have multiple GPUs on the same node. Okay, so far the model that we've been dealing with is where we have a CPU and a GPU, and then the CPU offloads work to the GPU. But in fact, we can actually have a CPU connected to multiple GPUs. And if we have a CPU connected to multiple GPUs, the CPU will need to somehow tell each GPU what to do and orchestrate the work across the GPUs. So there is support for doing this inside of CUDA. You can figure out how many GPUs you have on the node using something like CUDA get device count. So this API call tells you how many GPUs you have. And then you can use CUDA set device to select one of them. So you can have different devices if you want to, for example, launch a kernel on GPU 0, you can set the device to 0 and then launch the kernel. If you want to launch the kernel or call the kernel to launch a grid on GPU 1, then you can do CUDA set device for GPU 1 and then launch the grid on GPU 1. Now, typically, when we use multiple GPUs in a single CPU, we also use multiple CPU threads. And we have the CPU thread, each CPU thread being responsible for operating one of the GPUs, or calling kernels or copies or whatever for one of the GPUs. For multi-threading, we usually use something like OpenMP, or there's other multi-threading libraries that you could also use. So you can use multiple CPU threads, and each CPU thread would select one of the GPUs and operate one of the GPUs. And then you can also synchronize across the different GPUs using the CPU, or as we'll see later, we can also use shared memory across the GPU. Okay. Now, this is one way to synchronize. This one form of multi-GPU programming is where we have multiple GPUs attached to one CPU, but we can also have multiple GPUs on multiple different nodes in a network. So we can have multiple CPUs connected via a network, and then each of these CPUs could have multiple GPUs. And in this case, I would want to coordinate work not only across multiple GPUs that are connected to a CPU, but I also have multiple GPUs connected to different CPUs on a network. And in this case, we typically use something like MPI, which is the message passing interface library, or MPI allows us to be able to program multiple CPUs connected over a network. And we can have in MPI, we have something called a rank. So an MPI rank is like different threads on the CPU, but a rank would be running on different CPUs. And we can have each MPI rank. We can also have multiple ranks on the same CPU. So each one of these would correspond to a process that's running on the same CPU. And we can have each rank interacting with one of the GPUs. Now, one important consideration when we do multi-GPU programming on a network is that, so when we're programming multiple GPUs on a CPU, these GPUs, if I want to kind of share data across them, I can do it through the CPU memory, or I can do it directly across the GPUs, depending on how my system is configured. But oftentimes I can copy data from one GPU to another GPU using the CPU. And that's fast relative to if I want to copy data across the network. So if I want to share data from a GPU on one side of the network and one CPU on the network, and a GPU on another CPU in the network, what I would need to do is I cannot just copy from one GPU directly to another GPU. I would need to copy the data from the GPU memory to the CPU memory, then over the network to the other CPU memory, and then over the network to the other GPU. And this takes a lot of time, right? If I want to communicate across the GPU and one attached to one CPU and a GPU attached to another CPU, going over the network takes a lot of time. So one of the important considerations when we are parallelizing across multiple GPUs is how to overlap the communication across the network with the computation on the GPU. And one example of this, for example, is if we have some kind of stencil computation, and we divide the space that we're doing the stencil computation on across multiple GPUs, and each GPU does a portion of the space. Well, we have to share the halo elements across the different GPUs. So one thing people usually do is they will compute the elements at the boundary, and then while they're computing the internal elements, they would do the communication of the boundary elements across the network. So this is one example of how we can overlap the communication across GPUs with the execution of kernels on the GPU. Okay, so this is just a hint at how we program multiple GPUs and some of the challenges that we face when we do that. Another topic that we haven't really delved much into is interconnect. So when we have a CPU that's connected to the multiple GPUs, how are they connected? Well, they're connected via an interconnect, and one common interconnect that is used is PCIe. So PCIe is a type of interconnect that's used in many systems to connect CPUs and GPUs together. And CPIe is a very kind of general kind of interconnect. We use it to connect CPUs to GPUs, but we can also use it to connect CPUs to other kinds of devices like FPGAs, for example. And because PCIe is general, it's commonly used in many systems. But there's also other kinds of interconnect, like NVLink, for example. And NVLink actually provides faster interconnect, and we can use it to connect multiple GPUs together, or we can use it even to connect a GPU to some kinds of CPUs that support the NVLink interconnect. PCIe is very widely supported, so most CPUs would support PCIe, most GPUs would support PCIe. However, something like NVLink, only some CPUs support NVLink, and only some GPUs, particularly certain generations of NVIDIA GPUs, basically the later generations of NVIDIA GPUs, support NVLink. So PCIe is the general one. NVLink is more specific to NVIDIA GPUs and later generations of them, and is only supported by some CPUs. It gives you faster, and it's a faster interconnect, so we can get higher bandwidth when we are copying data between GPUs or between CPU and GPU. However, it cannot be used for anything. So if I want kind of something general that works for any CPU and GPU, then PCIe is usually the general interconnect that people use. Okay, any questions so far? Multi-GPU or interconnect? Okay, another topic is unified virtual addressing. So what is unified virtual addressing? Well, so far what we've been doing is we've had a CPU that had access to its main memory, and we've had a GPU that had access to global its own global memory, and we've been treating each of these as if it were its own address space. So the main memory is an independent address space from the global memory on the GPU. So if I have a pointer that points to an address, that pointer we've been assuming could point to that pointer value is going to be used here in main memory, or it's going to be used on global memory, and this would be its own virtual address space, and this would be its own virtual address space. So the pointer would point to different things if I used it here or if I used it here. But in fact, what later GPU systems or NVIDIA GPU systems did is they have something called a unified virtual address space, where we have a single virtual address space. We still have two separate physical memories, the main memory of the CPU and the the global memory of the GPU or the device memory of the GPU. We still have separate physical address space, but we have a unified virtual address space where the same so we have the same virtual address space that is used across the hosts and devices. And what that means is that an address, a memory address that points inside of the range of addresses that's supported by the main memory of the CPU is mutually exclusive from the range of addresses that's supported by the GPU. So the same memory address cannot be valid in both places. It's either valid on the CPU or valid on the GPU. Of course, even when we didn't have a unified virtual memory, it's probably not a good idea to use the same memory address here and here, because if I allocated some memory on the CPU and it incidentally pointed to valid data on the GPU, that doesn't mean I should be using that, okay? Using that memory. However, because the only reason that a pointer would be valid in the other address space is if I accidentally had two things mapping to the same address location. But that's not even a concern in when we have unified virtual address spaces. And the reason is that the address ranges are mutually exclusive. Now, what's the advantage of having a pointer, having a unified virtual address space across CPUs and GPUs? In other words, having the address ranges mutually exclusive, such that pointers I can't alias pointers across. Well, the advantage is that when I know that the CPU is going to use a separate virtual address range from the GPU, then I know I can tell where a pointer points to, whether it points to a CPU memory or GPU memory, from the value of the pointer itself. Okay, so the data location is known from the pointer value. So so if I have a pointer, I can look at the value of this pointer and I can say, oh, this range of addresses is the CPU memory, this range of addresses is the GPU memory. So by simply looking at the value of the pointer, I can tell if this pointer points to the CPU or the GPU. And the advantage of that is that when I do CUDA copy, remember when we did CUDA copy, we had to specify whether we want to copy from host to device, or we were copying from device to host, or maybe there was device to device or host to host. Well, with unified virtual addressing, we actually, with a unified virtual address space, we don't need to tell the runtime system whether a pointer points to the device or points to the host, because the runtime system can tell from the value of the pointer whether the pointer points to the device or the host. So if we are using unified virtual address space, then in our CUDA copies, we would not need to specify device to host or host to device. We can simply write CUDA copy default, and from the value of the pointer, the runtime can figure out whether this pointer points to the device or the host. So this is the advantage of having a unified virtual address space across CPU and GPU, where the main memory of the CPU uses a certain address range in the virtual address space, and then the GPU, the device memory in the GPU uses a separate address range in the virtual address. Okay? Is it clear to everyone? Any questions? Now, there's another advantage of unified virtual addressing, which I will show you. I will also show you. But let me first introduce another topic, which is zero copy memory. So, what is zero copy memory? Zero copy memory enables to have threads running on the GPU, so device threads, directly access the host memory. Okay, what does that mean? I have so far we've been saying that threads on the GPU cannot access data that's in the main memory of the CPU. I have to copy the data from the CPU to the GPU. Well, it turns out that we can use something called zero copy memory. And what that does is that here, zero copy refers to the fact that we don't have to do any CUDA copies. Instead, what we can do is we can have a thread that is running on the GPU access data access data that is in the CPU memory. What happens when we do something like that is that when a thread running on the GPU tries to access a memory address range, a memory address that points to data that is on the CPU, the runtime system on demand will copy that data from the CPU memory to the GPU memory and serve it to that thread. So rather than us having to do a CUDA copy explicitly, we can just allocate the data but of course there's a special way to do it. We can't just use the regular CUDA malloc, but we can. The idea is that we can allocate the data and then not copy it, but instead have the CPU thread, once it accesses that data, the runtime system will copy that data from the CPU to the GPU on demand. Okay. Now, an important thing here is that if the CPU thread is going to access data that is going to access data that is on if a GPU thread is going to access data that is in the CPU memory, and that data is going to be copied on demand, that means I'm going to be using a DMA to copy that data, right? So what does that tell me about the data that's in the CPU memory that I'm accessing? Where does it have to be?
In pinned memory.
In pinned memory, exactly. So the memory, for zero copy memory to work, the data that I want to be able to access from the GPU, the data that I want to be able to access from a GPU thread in the CPU memory should be allocated in pinned memory. Okay, and the way we do that is using an API call that is CUDA host alloc. Okay, CUDA host alloc. So this command CUDA host alloc, when we use it to allocate memory, what happens is that it gives us a certain memory range in the GPU that is in the CPU that is pinned, and not only is it pinned, but also if I try to access this data from the GPU, the runtime system will automatically copy this data for me from the CPU to the GPU. Now, without unified virtual memory, what we need to do is we need to get the data that we want to access in the CPU memory. We need to have it also mapped to the address space of the GPU. So what we can do is we can use a command called CUDA host get device pointer that takes a pointer that was allocated using CUDA host alloc that points to a pinned memory on the CPU, and gets a corresponding pointer on the GPU that the GPU can use to access this data. However, this over here is unnecessary if our system supports unified virtual addressing. So if I have unified virtual addressing, that means the pointers on the CPU and the GPU are mutually exclusive. Okay, so the pointer that I get from CUDA host alloc, I can simply give that to the GPU, and when the GPU dereferences this pointer, the GPU knows from the value of the pointer that this memory is actually in the CPU, not in the GPU. So it knows that it has to go to the CPU and fetch that data on demand. However, if I did not support unified virtual addressing, then the GPU would not be able to know from the value of the pointer whether this points to CPU memory or GPU memory. So this is why we would need to use something like CUDA host get device pointer to translate the pointer that points to CPU memory into something into a pointer that's usable on the GPU that the GPU can use to figure out that it has to go to the CPU to get that memory. Okay. Is this clear? Any questions about zero copy memory?
Professor?
Yes?
Would this give us some kind of like automatic pipelining of some sort, or not really?
So the combination of zero copy memory and unified virtual addresses, the combination of these two things gives you the feeling that the CPU and the GPU are accessing the same memory location, right? You don't have to worry about copying back and forth. Now, your point is a very good point. Does this give us automatic pipelining? And it kind of does, because what happens is, since I'm not copying and the copying happens on demand, then what happens is when some threads get scheduled on the GPU and they start accessing the CPU memory, what's going to happen is that CPU memory is going to get copied when those threads execute, when those threads request it. So here, because you have this kernel that's running and this memory is being copied on demand, some threads, they will make a request, that request will be served, and as soon as that request that data is copied from the CPU to the GPU, those threads can start executing without waiting for all the other threads' data to get served. And then the other threads will then later on come and make requests, and their data will start getting served. And what that means is that we're no longer waiting for all the copy to happen, all the input to get copied before any of the threads start working. The copies will happen on demand when the threads request. So the threads that request them earlier, the data will be copied earlier, and then the threads that come and request later, their data will be copied later while the earlier threads are doing their computation. So yes, you are right in that this gives us the feeling, this somehow does some of the pipelining for us. Now, whether this will be as efficient as doing the pipelining yourself, where you have more control over what's getting overlapped with what. That's something that you would need to try and see whether whether using zero copy memory and unified virtual addressing will give you as much of a benefit as doing something like doing the manual pipelining yourself. But it is a very good observation that we do get some kind of pipelining when we use zero copy memory and unified virtual addressing.
Okay, thank you.
Yeah, you're welcome.
Professor,
Yes.
when we use zero copy memory, do we get better performance than if we had copied everything ourselves to the GPU? Like, are we guaranteed almost an improvement?
So it really depends. It really depends on the situation, right? So if you have a case where you have this huge data set and you're only going to use a small portion of this data set, but you don't really know ahead of time which portion of this data set you're going to use. That's going to depend on some runtime information. So in this case, using zero copy memory is useful because you're going to be copying at runtime, so you end up copying only the data that you actually need, as opposed to having to copy everything and then only use some of it. Also, you can you get this automatic pipelining that somebody else pointed out, where you have this automatic pipeline that's taking place where you get more overlap between computation and copying by using them. However, you have the trade-off in that when you use CUDA memcopy, right, you're doing the copy in bulk. So there's some overhead that the system can amortize across the copy when you're doing this copy in bulk, right? Whereas having to do the copy, in pieces and pieces at a time, maybe each of those individual pieces will be faster, but there's going to be kind of a price that you're going to pay every time you need to copy a piece. Okay, so you have less amortization of that fixed cost. So it really depends on the situation, whether doing the copy in bulk and then computing is faster, or doing the copy on demand is faster. Okay, and that relates to first how many portions of your data what percentage of your data set do you need? Are you going to be using all of it, or are you going to be using only a small part of it that you don't know ahead of time? And also, how important is overlapping copying with computing?
I see. So for something like matrix multiplication, it's hard to say from the start whether the bulk copying compensates for the for having to copy into the GPU in the first place, right?
Right. So for matrix multiplication, the CUDA-MEM copy takes a very small fraction of time compared to the actual computation, right? Because the data you copy is n squared, but the computation is n cubed. However, if you're going to use zero copy memory, it means you're going to incur this this copy every time you want to access this matrix, or maybe it gets cached. However, it's hard to reason about. You would need to try it out, but it's hard to reason about whether you would actually get benefit from using zero copy of memory there, just because the copy doesn't really take much time compared to the actual computation.
I see. Okay, thank you.
Okay. Yeah, you're welcome. So one benefit, though, from doing this is that it makes the host code much easier, right? You don't have to worry about doing all these CUDA-MEM copies back and forth. You just allocate data on the CPU, then you go use it on the GPU, then you come back and use it on the CPU, then you go back and use it on the GPU, and the system is taking care of doing the copies back and forth for you whenever you need to. So in terms of the ease of programming, it makes your application much simpler if you use unified virtual memory. And in practice, the unified virtual memory or unified virtual addressing and zero copy memory is used very widely. And a lot of times people consider that if it was going to have a performance penalty, that performance penalty would be small enough that the benefit you get from making your code simpler is worth it. So this is actually used very commonly. The reason we don't teach it to you at the beginning of the semester is because we want you to be aware of what's going on underneath. We want you to be aware of the low-level details, and that's why we teach you CUDA-MEM copy in the course. However, in real applications, unified virtual addressing and zero copy memory together are used very frequently for people to simplify their code and also, in some cases, maybe even get good performance. Okay, clear?
Okay, thank you.
Yeah, you're welcome. Okay, another topic is events. So far in all the code that we've been writing, we've been synchronizing after every copy and kernel call in order for us to collect timing information. And I've been doing this just to keep the code simple, because I didn't want to introduce events from the very beginning, because I would have had to introduce streams at the very beginning, and I didn't want you guys to worry about streams from the very beginning. So we've been synchronizing after every copy or kernel call in order for us to collect the timing information. But in practice, this approach interferes with the execution and slows things down. I really don't want to synchronize across every time I have every time I do a copy or a kernel call, especially if I'm using multiple streams and these kernels are supposed to be executed in parallel with each other, or the copies are supposed to be executed in parallel with each other. So the way that we can collect timing information without having to do something like a CUDA device synchronize is using events. And events can be used to collect timing information without synchronizing by simply adding the events to streams in order for us to collect timestamps whenever something in that stream starts or finishes. So the way we can use events is like this. We can write CUDA event create, for example, to create an event. We can write CUDA event record to record an event, and we provide the stream we want to record into. Okay, so here we can, if we add an event to a stream, what we do is the event will simply capture the time when it's the event's turn in the stream. And then we can do something like CUDA event synchronize. So wait for some event to happen. So if I have multiple things inside of, if I put multiple things in a stream, and then I put an event, and then I put multiple things after the event, and then later on, I want to wait for the event to finish, but I don't care about waiting for the things after the event to finish, I can do something like CUDA event synchronize, which waits for a particular event in the stream to finish without waiting for the things that are after the event. And this is better than just doing CUDA device synchronize, which basically waits for everything that passed to finish. So maybe I want to wait for certain things in the past to finish without other things in the past to finish, and I can use events to do that rather than having to wait for everything. We can also get the elapsed time between events. So we can use CUDA event elapsed time to get the time in between two events. So for example, if I want to get the time between, if I want to take time how long it takes to do a certain CUDA mem copy, but I don't want to synchronize after that CUDA mem copy. It could be an asynchronous CUDA mem copy. And I don't want to synchronize to time it. I just want to time how long it takes without having to synchronize before it or after it. What I could do is I could record an event before the CUDA mem copy and record an event after the CUDA mem copy, and then get the elapsed time between these two events. And this tells me how long that CUDA mem copy took without me having to synchronize it and interfere with the asynchronous behavior that I'm trying to do. And of course, I can use CUDA event destroy to destroy an event that I previously created. Now, a lot of this information we can also collect in the profiler. So the profiler also tells us how long kernels take to run, or how long mem copies take to run. So this information, all of it can be collected using in the profiler. But if for whatever reason I would also like to collect this information in the code itself, maybe I want to use it to make some kind of decision in the code, I can use events to do that. Okay. Is it clear? Any questions about events? You guys see where they're useful? Okay. Another topic is tensor cores. So tensor cores were introduced with the Volta V100 architecture, and tensor cores are basically programmable matrix multiply and accumulate units inside of our SM. So each SM has tensor cores that can be used to do a small matrix multiply and accumulate operation in one instruction. And the reason tensor cores are so important, tensor cores were especially important when deep learning took off. It was very important for accelerating deep neural network workloads. And the reason is that a lot of these deep learning workloads are just doing matrix multiplication. Okay, and being we saw how good GPUs are at performing matrix multiplication, but in fact we can do even better by using tensor cores, which are the specialized hardware that does a small matrix multiplication and accumulate in one instruction, rather than having to execute multiple load and multiple add and multiply instruction to do the operation. So the tensor cores give us a lot of speed up when we use matrix multiplication, but we have to use them explicitly using a certain API. So in the Volta V100 architecture, we have 640 tensor cores. Since we have 80 SMs, there's actually 8 tensor cores per SM. And each one of these 8 tensor cores is capable of doing a 4x4 matrix multiply. So it can do a D equals A times B plus C operation. Okay. Here, D, A, B, C are all 4x4 matrices. Any questions about this? Okay. The next topic we didn't get a chance to talk about is libraries. So there's many libraries that are part of CUDA or that are popularly used with CUDA that have common parallel primitives. A lot of the primitives that we actually use in the course are provided in libraries. So for example, there's a library called Thrust that contains primitives like reduction, scan, filter, and sort. Okay, we implemented a lot of these manually in the course, and that was an important exercise because we wanted to teach you how these different primitives work, where they're performant, where they're not performant, and just the principles that go behind optimizing them. But in practice, if you are writing an application, you probably wouldn't write a reduction or a scan or a sort operation yourself manually as part of your application. You can just call a library like Thrust, or there's also a Cub, which Thrust uses. So Cub is another one. You can call one of these libraries like Thrust or Cub, and they would just do the reduction or the scan or the sort or the filter operation for you. You wouldn't have to do it manually yourself. So a lot of times, some of the primitives that we're implementing in this course, you wouldn't have to worry about implementing them yourself in a full-fledged application. You would just call some of these libraries to do it for you. But the course wasn't about teaching you libraries. It was about teaching you concepts behind reasoning about how to parallelize code, and that's why we went and we implemented these ourselves. Okay. Another one is CU-BLAS. So CU-BLAS is used for basic dense linear algebra like vector addition, matrix vector multiplication, matrix multiplication. A lot of these operations, again, we implemented matrix multiplication in class, and the purpose of that was to teach you about some of the decisions and the challenges that go into parallelizing something like that. But in practice, if you're using matrix multiplication or matrix vector multiplication in your application, you would probably not implement it from scratch. You would probably use a library like CU-BLAS that already has a lot of very highly optimized implementations of these basic dense linear algebra routines. There's also NV-BLAS, which is a multi-GPU library that can do these dense linear algebra operations on multiple GPUs, and this is implemented on top of. Another one is CU-sparse. So CU-sparse does sparse dense linear algebra. So again, we looked at in the course, we looked at how to do SDMP, and we looked at different sparse matrix storage formats. And it turns out that we actually have a library that does all kinds of sparse linear algebra routines for us. So in practice, if you have an application that has sparse matrix operations that you need to perform, you could just use these built-in library functions to create these matrices and to operate on them instead of implementing them yourself from scratch. But again, the reason we taught you about them is so that you can appreciate the kind of process that you need to go through when you're optimizing these kinds of workloads, and that these principles are also useful in other kinds of workloads that you would want to parallelize that may not necessarily involve sparse matrix. Another one is CU-solver. So CU-solver is useful for factorization and solve routines. So if we're doing matrix factorization, and CU-solver is actually built on top of CU-BLAS and CU-sparse. Another one is CU-DNN, and CU-DNN is popular in is used in deep neural networks. It implements a lot of routines that are useful for deep neural networks. And as a matter of fact, if a lot of the frameworks that some of you are probably familiar with, if you've worked with deep learning before, so a lot of these frameworks like Caffe, MXNet, TensorFlow, PyTorch, these frameworks, a lot of them give you the option of running on the GPU. And the way that these frameworks are able to take your models and run them on the GPU is that underneath what they do is they call CU-DNN. So a lot of these frameworks for deep learning that are popular and that they use GPU to make your deep neural networks much faster, they simply use CU-DNN to accelerate your code. CU-DNN is actually a very popular library used indirectly by these frameworks. And CU-DNN itself also uses something like CU-BLAS, because DNNs themselves do all kinds of density neural algebra and other operations. Okay. Another one is NV-graph. NV-graph is useful for graph processing. It gives you different representations of graphs and operations you can do on graphs. There's CU-FFT for the fast Fourier transform, if you're interested in doing any operations that involve FFTs. And there's also NPP. So NPP is useful for all kinds of signal, image, and video processing. So all of these libraries are very useful and very widely used, and whenever you're writing GPU applications. A lot of the parallels that we covered in this course are actually implemented within these libraries. So a lot of times you would not need to implement these parallel patterns from scratch. You would be able to just use these libraries to do these operations for you. And building an application involves composing together a lot of the functions that you can find in these different libraries. But again, the reason we went through all these parallel patterns is so that you guys can learn about what are the challenges that we face, and what are the optimizations that we can apply when optimizing GPU code in general. And these principles that you learn are also useful for you if you want to implement some other custom application that is not necessarily built into any of these libraries. Okay. Any questions about these libraries? Okay, the next topic is about other programming interfaces. So in the course, we've been focusing on CUDA. However, CUDA is not the only interface for programming GPUs. There are other programming interfaces out there as well. One of them is OpenCL. OpenCL is similar to CUDA. However, it is open source, and also it's more portable across non-NVIDIA GPUs. So if you're there are other hardware vendors out there. There are other GPUs besides NVIDIA GPUs. I will talk about those on the next slide. However, if you're interested in targeting GPUs that are, if you're interested in having the same code to be able to run on NVIDIA GPUs as well as non-NVIDIA GPUs, OpenCL presents a more portable programming interface, whereas CUDA is very specific to NVIDIA GPUs. In fact, OpenCL code is not just portable across different GPUs, it's also portable across different devices. So there are actually compilers out there that compile OpenCL to CPUs, and there's also high-level synthesis tools that compile OpenCL to FPGAs. So if you're only interested in running on NVIDIA GPUs, maybe CUDA gives you is a little simpler than OpenCL. So if you're interested in just running on NVIDIA GPUs, maybe CUDA is enough. But if you want your code to be portable across different kinds of GPUs, and also if you want it to also be portable across GPUs and other hardware like FPGAs and CPUs, then OpenCL is a popular interface, programming interface to use. Okay. Another interface is OpenACC, and OpenACC is a directive-based GPU programming interface. So here, by directive-based, I mean something similar to OpenMP, where you just take your regular sequential code that has a bunch of loops, and you can annotate these loops in a certain way, similar to the way you annotate them for parallelizing on CPUs using OpenMP. And by simply annotating your loops in the right way using OpenACC, the OpenACC compiler takes care of automatically taking your sequential code and parallelizing it to run on the GPU. Of course, assuming that the loops you're annotating are parallelizable and everything. Okay. So directive-based programming is very popular in parallel programming. It's popular on CPUs. People use OpenMP all the time to parallelize work on CPUs rather than using lower level threading libraries like pthreads. And then similarly, if you don't want to have to worry about allocating memory and calling a kernel and dividing the work across blocks and all these things, you can use OpenACC to annotate loops in your sequential code in order for you to parallelize to have that code automatically ported to run on the GPU. Okay. Yet another library is C++AMP, and C++AMP is a library where you can use to implement GPU programs inside of C++. So you can inside of your C++ code, you can use Lambda functions and things like that, and certain special syntax in order for you to implement code that would run on the GPU directly in C++ without having all these CUDA extensions. Okay, so that's any questions about programming interfaces? Okay, the next topic is other GPU hardware. So in the course, we've been focusing on CUDA, and we've also been focusing on discrete NVIDIA GPUs. NVIDIA GPUs, meaning the GPUs that are manufactured by NVIDIA, which is a popular GPU manufacturing company. And by discrete, what I mean is GPUs that are not kind of integrated with a CPU on the same chip. You have a GPU that is a chip that is separate from the CPU. That's what I mean by discrete. The GPU is its own independent chip. But in fact, we have other GPU hardware besides NVIDIA GPUs. AMD manufactures GPUs. If you might be familiar with Radeon GPUs, these are manufactured by AMD, and these are also very popular for, NVIDIA GPUs are popular for gaming, and they're popular also for high performance computing. And AMD GPUs are also popular for gaming, and they're also popular for high performance computing. ARM manufactures GPUs. You might have heard of Mali GPUs and ARM. Some of these GPUs are used, ARM is very popular in mobile devices. So some of these GPUs in mobile devices are manufactured by, they're ARM GPUs. Sorry, I shouldn't say they're manufactured by ARM. There's many different companies that manufacture ARM processors, but the GPUs use are kind of follow the ARM architecture. And then also there is Intel GPUs. So Intel actually manufactures GPUs as well. Even though Intel is very known for CPUs, but Intel also manufactures its own GPUs. A lot of these actually come integrated with your within your machine. So you probably have, if you have an Intel processor, you probably also have an Intel GPU in your system that's used for controlling some of the graphics on your screen. Besides other GPU hardware, like I said, we've been focusing on discrete GPUs, but there are actually integrated GPUs where you can have CPU and GPU on the same chip, and in this case, the CPU and the GPU would share the same physical memory. And the advantage of this is that we don't have any data transfer over PCIe, right? You actually can access the same physical memory from both the CPU and the GPU because they are on the same chip. Okay, and AMD is the kind of one of the pioneers in manufacturing these kinds of. Okay. Any questions about this? Okay, and then the last thing I would like to mention is a disclaimer about all the comparisons I've been doing with CPU throughout the course. So far in the course, what I've been doing is we've been comparing GPU with CPU, but we've been using a single-threaded, non-vectorized CPU code. And what this does is it exaggerates the GPU speed up that we've been seeing. And for the purpose of this course, maybe that's okay, but in general, this practice is frowned upon if you're publishing a paper, for example, on where you're reporting your speed up between CPU and GPU. If we really want to do a fair comparison between GPUs and CPUs, it would be more fair to compare our GPU implementation to a parallel CPU implementation that uses vectorized CPU code, because it's just like a GPU can run many thread blocks in parallel, or many warps in parallel, a CPU can run many threads in parallel, and also a CPU, every CPU core, for many CPUs, every CPU core has a vector unit where we can vectorize the CPU code rather than just having having kind of a single thread running on the core. So we did not do this in the course, and the reason we did not do this in the course is because the objective of the course is not to focus on CPU parallelization, it's to focus on GPU parallelization. So I didn't want to trouble you with parallel computing on the CPU as well. This is something that you can cover in another course. Perhaps you've taken a course on this before this course, or you might take a course on this later, after this course. However, I want to say this because I just wanted to take the comparisons that we've been doing with CPU with a grain of salt, because in fact, just like we've been parallelizing and vectorizing on the GPU, we can also do the same on the CPU. So a more fair comparison with CPU would have been to compare to parallel CPU code that uses vectorization. Okay. So with that said, I've reached the end of the course. I'm sorry that I had to rush through all these topics today, and we didn't get the chance to look at them with more depth. But unfortunately, this is the number of lectures that we have in the course, and we've run out of time. So does anybody have any final questions before we conclude? Okay, well, if there are no final questions, then thank you guys for attending, and it was a pleasure having you guys in this course, and I look forward to seeing you in other courses or perhaps other research projects. Bye, everyone.